All right, what up, fam? Let's get going. We're gonna do this calculus review. Please note, while I'm going over this, I'm not really gonna be doing very much of the explaining as if it was a lesson. I'm just going to be doing the problems, explaining the steps as I go along. If you're looking for a longer lesson on one of the particular topics, please sure to be letting me know either in the comments, or you're allowed to email me too. Email is totally fine. Or if you happen to know, my Discord or something, just send me a message over Discord, and we will be able to help you out from there. But again, I'm just going to do the problems as is. So starting off with number one, using the limit definition of the derivative to find f prime of 2 if f of x equals x squared. So whenever you're doing the limit definition of the derivative at a point, so this is going to be at a point only, you are specifically going to be using the limit as x approaches a of f of x minus f of a over x minus a. The easiest way to remember this one is it looks exactly like your regular old slope formula, because that's what a derivative is, y2 minus y1 over x2 minus x1. And for this particular question, a is going to be equal to 2, and our function is going to be x squared. We are going to want to go ahead and figure out what our value is. So plugging in 2 into our problem is going to give us 2 squared, which is 4. And we're going to need that when we're actually plugging it in, because we need to figure out what f of a is up here. So immediately plugging it in for the actual problem, I think I'll just switch colors to a darker blue for the actual question. We're going to be doing the limit as x approaches 2 of f, just f of x, which is x squared. My oh my. F of x is in fact x squared. Minus f of a, which we figured out was 4, divided by x minus a, x minus 2. All right, so that's a regular old x. I apologize for my handwriting. That is just an x squared. After that, we're going to use our difference of two squares, because if I plugged in 2 immediately, I get 0 divided by 0. That is indeterminate, so we must instead do a little bit of factoring. The top is that difference of two squares. So we're going to have x minus 2 multiplied by x plus 2, all divided by x minus 2. And when you do that, the x minus 2's cancel out completely, and you end up with the x, limit as x goes to 2, of just x plus 2. And that's easy enough. You can just plug 2 into x there, and you'll get 4. Easy enough. Turns out the derivative and the original value are exactly the same. Doesn't happen too often, but it does occur sometimes. Let's move on to our next question, which is another limit definition of our derivative, but this time we are going to be doing it only if it equals the square root of x and it's just a function. So anytime it's an entire function, we use a different definition than the one I wrote before. This one's going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. Please note, if you want to simplify your studying, you could use just this one and simply make x equal to 2. And doing this entire process. But if you do that, you will have more algebra to do than the one I showed above. So I recommend not doing that for these ones. Regardless, when you're doing it, your limit as x goes to h. The function that we're working with in this case is going to be f of x is going to be the square root of x. Just to make our life easier, I always like writing out what f of x plus h is in advance. So that's going to be plugging in the x plus h actually in to where x is. That way now it's going to be a little bit easier for me to actually write my final version of the problem. And again, switching colors for the actual problem here, we have the limit as h approaches 0 of f of x plus h, which is x plus h under the square roots, minus f of x, which is the square root of x under the square roots, all divided by h. And there we go. In order to do this question, whenever we have a square root doubled up like this, you're going to have to multiply by the conjugate. The reason why is we should know from earlier in our math careers that a plus b multiplied by a minus b is going to be a squared minus b squared. And because you can also do this with square roots, that must mean that the square root of a plus the square root of b multiplied by the square root of a minus the square root of b is just going to be a minus b. In this case, what am I talking about? We have a square root of x plus h minus a square root of x. That's these two we're talking about here. We actually have the minus version. So if we multiply it by the positive version, we'll just get a minus b. The square roots are gone, and that is what we want to do. So we're going to go ahead and rewrite this. We have the limit as h approaches 0 of the square roots of x plus h minus the square root of x all over h, and you are multiplying it on the top and bottom by the conjugate, the square root of x plus h plus the square root of x divided by the square root of x plus h plus the square root of x. Oof, a little bit annoying there. I apologize, my handwriting's atrocious. I'm going to try to write bigger on the next line. Regardless, when we're doing this one, the top, when you multiply it out, just like I said, the square roots disappear, and we just have the two things subtracting from each other. So we end up with x plus h minus x. And on the denominator, we have h times this entire thing, which we are going to write inside of parentheses. We don't want to distribute because it's going to make our life harder by distributing, so we don't want to distribute there. Continuing on here, these are all equal to the ones above it. Now, if you notice, the x minus the x is going to cancel out, so we have just an h on the top. And I'm doing a little bit more copying here. There we go. And if you notice, now we have an h over an h. Those guys are going to cancel because it's all multiplication. So we can also cancel those. And now we have the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. So just plugging that in, then I can actually plug in that h equals 0, because now it will not cause any divided by zeros. I'll have 1 over the square root of x plus the square root of x, which simplifies to 1 over 2 square root x. And that is the way most teachers are going to prefer to write it. If your teacher is anti square roots in denominator, it could show up as something like 1 over 2 x to the negative a half. That's also acceptable, but this is like the more standard way of writing this particular derivative. I will say that the other one I personally think you should try for yourself, just because it might be on the test, aka if I was a calculus teacher and I made these two practice questions, I would probably be looking at maybe f of x equals 1 over x and making you do some fraction addition as the problem for practice. Not going to do that because that's not what's actually on the test. We're on the review here. Let's go on to question number 3, where it just says to take the derivative of x squared tangent of x. So here we go. This is question number 3. And it says to find your derivative of x squared times the tangent of x. For this particular problem, it is two things being multiplied. Whenever you have two things being multiplied, taking the derivative, we call it the product rule. The product rule says that if I have two things being multiplied, I'm going to say f for first and s for second, and you are trying to take the derivative of those two things. You can't even see what I'm writing here, but the derivative of those two things is going to be the derivative of the first, leaving the second one alone, plus the derivative of the second, leaving the first one alone. So in other words, you're going to be taking the derivative of both and multiplying by the original for both of them. So for this particular question, I think the easiest way to do this is to arrange it nice and neat first. So you have your f and your s. In this case, your f is x squared. Your s is the tangent of x. Your derivative of x squared is 2x, and your derivative of tangent is secant squared. If you haven't memorized stuff like that now, I don't know if I'm going to be able to help you for this calculus final, I got to be honest. And if you set it up this way with this derivative of the first times the second plus derivative of the second times the first, it actually ends up being kind of like your old school cross multiplying. You're going to multiply these two together, so you're going to have 2x multiplied by the tangent of x, because you're multiplying derivative of the first times the second, and then adding derivative of the second times the first, so plus secant squared of x multiplied by x squared. If it's like a multiple choice question, please note there's an x squared in both in both of these that could be factored out if you felt like it after the fact. But if it's not multiple choice, then you can just leave it like that as is. You do not need to simplify any further. Boom, let's move on to question number 4. So question number 4, we're looking at a derivative of the sine of x over x cubed. So this one, you actually have two choices. You could do the quotient rule, which is the one I'm going to do because it's kind of what I think most people are expecting. Or you could actually just do the one that we just did, a product rule, and you can make this into a product rule if you want to try it yourself. I will write what it's equal to. You could write this version of it where you do x to the -3 and then just do a product rule with my f and the s just like we did. And that's actually going to be faster in a large portion of the cases. However, this question was set up as practice for the quotient rule, and there might be a problem that you can't do this with. Like if I was writing this review, I would have done x cubed +2 or something like that. So there's not an easy quotient rule or easy way you could write it as a product rule to actually do the question. Regardless, because it's a quotient rule, the main idea here is that if I have two functions, I'm going to go ahead and call them the high and the low function. So a high and a low, numerator, denominator. But if you have a high and a low function, you're taking the derivative. It is going to be low d high minus high d low over low low. What in the world am I talking about here? Well, it's the low function times the derivative of the function on the top minus the high function times the derivative of the low function. So that's how I memorize it, is this mnemonic device. Low d high, kind of like that, minus, and then scrolling up a little bit, right there, minus high d low over low low, because low would be low squared. Anyways, that's how I memorize it. You don't need to memorize it that way. Regardless, setting this up, our high function here is going to be the sine of x. Our low function is x cubed. Our derivative of our high function is cosine of x. Derivative of our low function is 3x squared. And we are going to be doing low d high. So we have low d high. And another thing to notice, if you're doing the way I set it up originally with this f times s prime, and I multiplied these two together first, like that, it's going to work exactly the same way. You have low d high right here. So we're going to end up with x cubed multiplied by the cosine of x minus high d low minus these two, minus sine of x times 3x squared, all divided by low. In this case, going to be x to the power of 6, because you're doing x cubed squared. If you want to, you can leave it like that. However, one thing to note in this particular question is it really does make sense to simplify, because there's an x squared in all three terms here. So this can easily simplify to x multiplied by the cosine of x minus the sine of x times 3 divided by x to the power of 4. So I do think that makes sense to do. I kind of wonder, I have their answer key here somewhere. Let's see, what do they do? Ha! Look at this. This teacher's funny. Their answer there has or. Both of them are good, is what they're trying to say. I like that. What a great little answer key having both those answers. Anyways, I'm going on to question number 5. What I'm trying to say is I approve of this this teacher, whoever this is. Question number 5. Our derivative of the natural log of e to the x plus 3. By the way, anyone who just wants to know a little side fact about ln, why is it natural log? If it's ln, it's because in Latin it's the logarithmus naturalis. Obnoxious. Anyways, doing our derivative, we have a chain rule function. Anytime you have a function on the inside of another function, your general chain rule looks like this. If I have f of g of x, our derivative is f prime of g of x times g prime of x. And you can't even see what I'm writing. Of course, yet again, Mr. Richards, get it together. And what does this say? What this is trying to say is this part is the derivative of the outside of outside leaving inside alone. And then this part right here is the derivative of the inside. Derivative, whatever. That says derivative of the inside. So derivative of the outside, leave the inside alone. So in this case, our f function is this outside, this ln. Our inside function is this e of x. Our derivative of ln is 1 over x, but we're going to be leaving the function alone. So it's going to be 1 over e to the x plus 3. and then we're going to multiply it by the derivative of the inside function. The derivative of the inside function is e to the x plus 3, and the derivative of that is just e to the x. And this has an obvious simplification of e to the x over e to the x plus 3. Boom, boom, boom. Question number 6, same exact concept. Question number 6 here is we have our d over dx of e to the cosine of x. And same exact concept. Our outside function this time is our e. Our inside function is cosine of x. So derivative of the outside, leaving the inside the same. Derivative of e is e, so we can just copy it. Multiplied by the derivative of the inside. Derivative of the inside is negative sign. Do be careful with that. Could be easy to make a mistake. I think if you're simplifying this, you probably want to move the negative to the inside there, but I'm not going to worry about it. And I think I am done talking about our chain rule question there. Okay, question number 7. Here you go. So this one is a junky one. I don't like this problem. The reason why I don't like this problem is you have to do a little bit of memorizing for it. Your derivative of the inverse sine, so like our regular old derivative of inverse sine is 1 over the square root of 1 minus x squared, and you just kind of have to like know that off the top of your head in order to do this question. The other way you can do this problem is with implicit differentiation, but that's already part of your lesson later in numbers 8 and 9, I can see. So I think this one you're just supposed to have it memorized. So the idea is you're going to take this x squared and you're going to slot it into this x squared there. So we have 1 over the square root of 1 minus x to the power of 4. And then you're going to be multiplying it by the derivative of the inside, which is just 2x. So you can simplify this to like 2x over the square root of 1 minus x to the 4th. There are other ways to do this question, like I said, with implicit differentiation that kind of make more sense, but it's a heck of a lot longer. Good luck. Have fun memorizing all your inverse sines. I don't have that great of advice outside of you are able to do this by hand if you need to, like a longer method. But I mean, you're in the middle of final, you got to move fast. So I wouldn't worry about it. I would just memorize it. All right, number 8. Let's move on to the next question here. So implicit differentiation, it says dy over dx if, and we're looking at the cosine of x plus the sine of y equals 2. Your general rule of thumb whenever you're doing a question like this is take derivatives of everything, but when there is a derivative with y, multiply by dy over dx. All right, so what am I talking about? The derivative of cosine is negative sine. You should already know that. Derivative of sine of y. Sorry, my dog is walking all over the papers I've thrown to the floor. All right, so derivative of sine of y is going to be the cosine of y, but following the rules we just wrote is anytime you take a derivative of everything, but when there's a derivative with y, you multiply by dy over dx. And the derivative of 2 is 0. From this point here, you just need to solve for dy over dx by itself. So we're going to go ahead and add sine of x to both sides. I got ahead of myself saying tangent because I kind of know what the answer is going to be here. So all I did there is I added sine of x to both sides. Now I'm going to go ahead and divide both sides by cosine, and we get a version of tangent, not actually tangent because it's 2 different letters. But yeah, we get sine of x divided by the cosine of y, and that's it. Same exact concept on the next one, except we're going to have a product rule with it, so that's going to be a little bit annoying. We're going to have a double product rule. So I show extra work on this. Please note, if you are a star calculus student, you do not need to show nearly as much work as what I am showing, and it is completely optional to show whatever work there is. How about this? I'll show the work for the first one, but not the second one. That would be a cute thing to do. All right, so we have double product rules. So our first one is x. Our second one is y to the third. So our derivative of x is just 1. Our derivative of this one is 3y squared. But don't forget, we did a derivative with a y in it, and therefore we need to put dy over dx as a multiplication afterwards. I said I was going to only do one step of work. I'll just do both of them. It can't hurt. Our other first one is going to be x squared. That derivative is 2x. Then we have an s is y, and our s prime is 1, multiplied by dy over dx. Anyways, let's do our actual derivatives now. It is the derivative of the first, leaving the second one alone. So we're going to have just y cubed, adding these two multiplied together. So x times 3y squared times dy over dx. Plus, now we have this one to deal with. So we have these two multiplied, 2xy. And then these two multiplied, the 1 doesn't need to be written, plus x squared times dy over dx. And derivative of 8 is 0. Oof! Did it. Now we have to actually solve for dy over dx. So anytime you're solving for a variable, remember you want to move everything that has the variable to one side, everything that doesn't have the variable to the other. So we're going to go ahead and copy these two down. We don't need to do anything with them at all right now. Okay, we copied them. Now we're going to go ahead and subtract these ones. So minus y cubed minus 2xy. Then we're going to go ahead and factor out a dy over dx from both of these terms. And last but not least, we're going to go ahead and divide by this conglomerate here, and we'll have our final answer. Like I was saying before, this might be one where we want to check our answer key with a different question. So let's see, what do we got here? And where'd my answer key go? In my pile of paper the dog was walking all over. Let's see what we got. Is that exactly what I have? That is exactly what I have, except they've moved the 3. That's kind of probably a better positioning of the 3. But there's no difference with these answers, and I am satisfied with how I wrote it. All right, boom, boom, boom. Let's move on to our next question. So find equation of the line tangent. This is like almost exactly the same stuff, except this time it wants to have our tangent line. So it wants tangent line, and it's y equals x squared plus 3 at 2 comma 7. Please note they did not need to give you the 7 of this. They only need to give you the 2. If they didn't give you the 7, you'd have to plug the 2 in. 2 squared is 4. Add 3, you get 7. So our tangent line, main concept for any line is we always want to use our point slope formula in calculus. So we have y is equal to our m multiplied by x minus x1 plus y1, except the way that we're going to be writing this is that our tangent line will be f of x is equal to our derivative at some coordinate a that we're interested in, multiplied by x minus a plus f of a. So it's exactly the same. The third time I've done this. All right, sorry guys. So we have, again, our point slope form, m times x minus x1 plus y1, and we're just going to be rewriting this. So our y is going to be f of x, our m is our derivative at some point a, x minus that a value plus the y value. In this question, here is our a and here's our f of a. So the only thing we actually need to find is our derivative at the point a, and we'll be done. So our derivative here is just going to be 2x, and our f prime of 2 in this question is going to be 2 times 2 is 4. We actually already did that question earlier in the day in a way. So we get 4. Our final answer now, f of x is equal to 4 multiplied by x minus 2 plus 7. If your teacher requires it, you can also distribute and add like terms. I don't care about that. Moving on to the next question, number 11. So 11 is same exact thing, equation of the line tangent at for y equals 1 over x at 1 comma 1. So first of all, when you're rewriting this one, our original function here is going to be x to the negative 1. That's the excuse me, much easier way to write this particular problem. So our derivative now, using our power rule, we're going to have negative x squared, x to the negative 2, sorry. And you're just plugging in 1, so it turns out our derivative at 1 is just negative 1, because you're plugging in 1. 1 to the negative 2 is still 1. And using our formula from above, our equation of our line tangents, f of x is going to be equal to our negative 1 slope that we just found, x minus the original 1 plus the original 1. Lots of 1s all over the place in this question. Moving right along, number 12. Oof. All right, so number 12. I don't like questions like this, number 12 and 13. And the reason why I don't like questions like this is that they're very difficult to teach. The way that you teach these questions is your general steps in doing these problems. I don't like writing these down, but I know that it's the best way to do it. So step 1 is draw a picture. Step number 2, write down all known information. All known info. 3, take d over dt derivatives. 4, plug stuff in and pray it works. Plug stuff in and pray. Or, if you're not into praying, then, whatever it is that you do. All right, draw pictures, write down all known info, take these derivatives, plug it in, and, hoping Cthulhu is on your side. We have this question of a 10-foot ladder is leaning up against a wall. So here's my beautiful brick wall. There's my wall. Okay, we got a wall. And we have a ladder that is leaning up against the wall. So here is my ladder. There's my ladder. And the ladder is 10 feet long. So we'll put the feet on there. At the bottom of the ladder is sliding away from the wall at 2 feet per second. All right, so we have basically a ground here, and this ground is moving this way at 2 feet per second. How fast is the top of the ladder moving up the wall? So in this case, if you notice, I have an ft over s. That's because it's a rate of some kind. So this is already a derivative. This is not a derivative. This question wants to know how fast is the ladder sliding down the wall. So I'm going to go ahead and give this a value of x. I'm going to give this a value of y. And we want to know what is dy over dt, the rate of change of y with respect to time, when the ladder is when y is equal to 6. All right, so there's my picture. I wrote down not all the information yet. I wrote down a bunch of the information. By the way, this is dx over dt if you wanted to know. All right, because it's how much our x is changing by. We do have a piece of information we haven't written down, and that is our Pythagorean theorem. We know that x squared plus y squared is equal to 10 at all times, because we have a beautiful little right triangle there. All right. Now we have to do take d over dt derivatives. What that means is very similar to our differential equation, our implicit differentiation earlier. We're going to take the derivatives of everything, except now we're going to put a d, whatever the letter is, over dt. So for instance, the derivative of x squared is 2x, and then we're going to put a dx over dt. The derivative of y is 2y, and now we put a dy over dt. And our value over there is 0. Derivative of 10 is 0. After that, we don't need these 2's. You can divide everything by 2, so the 2's are kind of just gone. So I'll rewrite this one more time without any 2's, because those are a waste of time. And all the other information you're going to be able to figure out, because you're told that dx dt is always 2. You're told that y is 6 right now. dy over dt we do not know. That's what we're trying to figure out. But what's x going to be? Well, if y is 6, then we have one of the most basic triangles in the world. We have a 3, 4, 5 triangle. If you don't know what I'm talking about here, there is a trick to a lot of these problems that teachers make happen. So we have a side of 6, a side that we don't know, and a side of 10. If I divide both of these by 2, I get a 3 and a 5, but there's that 3, 4, 5 triangle. So if I could divide by 2, I can multiply up here to get 8. and that's like the fast way to figure out that this guy is an 8. If that did not make sense to you, what you could have done is instead plug in the 6 here, and you could have just like solved an equation, you know, x squared plus 6 squared equals 10 squared, and then done, you know, x squared plus 36 equals 100, x squared equals 64. Okay, x is equal to 8. Whatever. Point is, we can solve this equation now. We have 8 times 2 is 16, moving it to the other side. We're going to have 6 dy over dt is equal to negative 16. And our final answer, dy over dt, is negative 16 over 6, which simplifies to negative 8 over 3. We wrote down the units somewhere before. Don't forget units on these. It's a silly reason to lose points. Negative 8 over 3 feet per second. And just to make sure I didn't make a mistake, I am going to be checking my work on this one. What do we got? I'm a little bit mad. They used a decimal. Unacceptable. Cut from the team. We're using fractions here. No decimals allowed. All right, moving on here. I need to pause the video and get more paper. All right, we are back, and this one, by the way, if you missed the previous question, that's what it says. This number 13 is circular oil spills increasing in area at a constant rate of 100 square feet per minute. How fast is the radius increasing the circles 4 feet? Okay, so I said to draw a picture every time. I don't think you really need to draw a picture, but, you know, if it helps you, okay, you have this thing increasing in size. There's our oil spill increasing in size, and you are told that the rate of change of the area is 100 square feet per minute. So 100 feet squared per minute. So that is the information that they gave you. And you want to know how fast the radius is the radius increasing. So how fast is dr over dt when r equals 4. So the only other piece of information that you have not written down at this point in time is the area of a circle. The area of a circle is one you should know. It is pi r squared. And we had to take the derivative of all the stuff that we wrote down. So we have dA over dt is equal to 2 pi r times dr over dt. We just did 2 in front, power rule stuff. And we're told that the area is increasing at 100 feet per second squared. Then we have 2 multiplied by pi. We're told that the radius is 4 times dr over dt. And last but not least, we're going to divide everything 100 over 8 pi. So 100 over 8 pi is equal to our dr over dt. We do need to simplify that, though. Is that 50 over 4, 25 over 2. So 25 divided by 2 pi, and that is going to be feet per minute. Note how I don't have the squared on that one is because area is feet squared. This is just regular old radius is our dr over dt. And I saw in the answer key that they did use a calculator on it, which is kind of silly. Our calculator for the first time today, we got 25 divided by 2 pi. Almost forgot a parenthesis there. We get 3.97, which was the answer in the back. All right. Either way, I prefer the exact answer, and I wouldn't be surprised if your teacher does too. Number 14, here we go. On to question number 14. I hope you were able to read all that stuff as I was doing it. I don't know if I slid it all down or not. Whatevs. All right, number 14, show your work. Given the function f of x equals x cubed minus 12x plus 1. Find all critical points. So part A here, we want those critical points. Critical points, remember, definition of critical points is when your derivative equals 0 or dne. So you got to figure out one of those two situations. So in this case, this is a polynomial, so derivatives are going to exist everywhere along with the second and third, whatever derivatives. So you don't have to worry about dne's at all for this particular question. You only have to worry about dne's when it's a rational function, you have an x in the denominator, or a function that has a non-defined domain, such as natural logarithms and things like that. Either way, derivative equal to 0. So our derivative, first of all, is going to be just 3x squared minus 12. and we are setting this equal to 0. In the process of setting this equal to 0, let's go ahead and factor out a 3. We got x squared minus 4, and then factor some more, x minus 2, x plus 2, and therefore for our 0 is going to be equal to x minus 2, or 0 is going to be equal to x plus 2, so x is equal to 2, or x is equal to negative 2. You could have also done this one by like adding 12 to both sides, dividing by 3, taking the square root, and remembering your plus or minus sign. That was also an acceptable way to do that question. Regardless, here are our critical points. The actual critical points, though, you do need to actually plug them back into the original function, so we need to figure out what f of 2 is. F of 2, what is that going to be? 8 minus, I'm using a calculator. I'm done. All right, we have 8 minus 30. Oh my god, this is what I'm talking about. 2 to the third. That was 8. Why did I not just type 8? Minus 12 times 2 minus 1. Yeah, plus 1. Jeez, I could have done this in my head. Anyways, you get negative 15. So our first critical points for our letter A is going to be 2 comma negative 15. But you could have also plugged in a negative 2 instead. So going in here, second insert a negative sign. Second insert a... Oh my gosh. Okay. Calm down, 17. Anyways, those are our critical points. After that, letter B. Letter B, determine all intervals of increasing and decreasing. Typically, what they want to see for work on this question is going to be a number line where you have your derivative number line, and your derivative number line is going to have the 2 critical points as your x values, and then you're kind of dividing it up into 3 sections, and you divide those sections up upon where those critical points are. You need to pick some numbers that are in each section. So for instance, between negative 2 and 2, I think the easiest value is 0. Above 2, I think the easiest number is 3. Below negative 2, I think the easiest value is negative 3. Then you plug these numbers in to the derivative. So we're looking at our derivative at negative 3. We're looking at our derivative at 0. And we're looking at our derivative at 3. Again, these numbers were arbitrary. You could have picked like a 1 or a half or whatever. You're picking any number in those sections. F of negative 3, we only care if it is a negative number or a positive number. So for instance, if I just plugged in 3 multiplied by negative 3 squared minus 12, again, I'm plugging it directly into that derivative that I calculated earlier. It's going to tell me it's 15. Because it is a parabola, this is also going to be 15, and if I plug in 0, I get negative 12. The point is, though, I don't even care about what these numbers are. I only care if they're positive or negative. So it's positive in this section, it is negative in this section, and it's positive in this section. Or in other words, your increasing is going to be where the derivative is positive, and your decreasing is where the derivative is negative. So we're looking for our final answer on this one. We can say our increasing... I for increasing, of course. There's not 2 i's. Increasing is going to be negative infinity. There's a negative infinity there, positive infinity there. Negative infinity to negative 2, our critical point. I need to drink of water. Union with our 2 comma infinity. And then our decreasing section is just going to be this smack dab in the middle here, negative 2, comma 2. Please note, for increasing, decreasing, if your teacher is a reasonable human being, you never use brackets. You only use parentheses for increasing and decreasing, because you're neither increasing nor decreasing at the critical points. From there, we also need to do letter C. We're not even done with this question. We got to go letter C here, find all the inflection points. So letter C here, our definition of inflection point, if you did not know, an inflection point is going to be when f double prime of x changes sign. So plus to minus or minus to plus. So our original function was x cubed minus 12x plus 1. We already figured out our derivative was 3x squared minus 12. And our second derivative is going to be just 6x. So in this case, our only point of interest on our second derivative number line is 0, because that's the only time where, if I solve 0 equals 6x, then x equals 0. That's the only case. And also it's super duper obvious because it's a really boring straight line that if I divide it in half over here, it's a concave up on the right and concave down on the left. And because it changes sign negative to positive, there's an inflection point at 0. So plugging 0 into the original equation, f of 0 is equal to 1. So our inflection point is going to be 0, 1 for our inflection point. Letter D, intervals of concave up and concave down. We pretty much already did that. Our down part is going to be negative infinity, 0, and our up part is going to be 0, infinity. And again, you can put that negative infinity over here, the positive infinity over there, and move on with your life. I'm done with this problem. We're moving on to question number 15. Compute using L'Hopital's rule. L'Hopital's rule is where it's at. All right, number 15, we got L'Hopital. Our L'Hopital of limits as x goes to 1 of the ln of x over x minus 1. L'Hopital says that if you have a limit that equals 0 over 0 or infinity over infinity, and there's there's more of them. It's like infinity, you can't even read. Oh yeah, you can. Or infinity minus infinity, or a whole bunch of other ones that I don't even know if you have to cover them in your class. There's like 1 to the infinity. There's 0 to the 0. There's other stuff. The point is there are other indeterminate forms that it could be. I think these are the only ones that are in a typical Calc 1 course. If I'm wrong, I'm sure you have your notes to worry about. So the first thing you have to do for any of these problems is show that you have 0 over 0. So you have the ln of 1 divided by 1 minus 1, which is 0 over 0, which implies I can use L'Hopital's rule. L'Hopital's rule says that this original limit is now equal to the limit with the derivatives separately, not the quotient rule. So you're not doing the quotient rule, you're doing our separate derivatives. Is the same as the limit as x goes to 1 of 1 over x, that's the derivative of ln of x, over 1, the derivative of x minus 1. So derivative of the top, derivative of the bottom, two separate things. And now I can plug 1 in, and it's trivially 1. Moving on to question number 16, exactly the same concept. We have the limits as x approaches 0 of 1 minus the cosine of x over x squared. So in this case, I would have 1 minus 1 over 0 squared, which is 0 over 0, which means I can use my L'Hopital's rule. So because I can use my L'Hopital's rule, I'll do the limits as x approaches 0. The derivative of negative cosine is positive sine of x, and the derivative of x squared is 2x. And now I can plug in 0, and I get 0 over 0, which means I can do another L'Hopital's rule. So I'm going to do another L'Hopital's rule. So I got limit as x goes to 0, derivative of sine is positive cosine of x. The derivative of 2x is just 2. So plugging in 0 into this, I get 1 over 2, and I'm finally done with the problem. Moving on to the number 17, find if f of x equals this and f prime of this. We got a differential equation, or I don't know, an initial value problem, an IVP, as they say. So we have our let's write right there. Okay, if we have f of x, f prime of x is equal to 6x squared minus 5. And we are told that f of 1 equals 3. All we're going to do here is we're going to do the antiderivative on both sides of the equation here, and we're going to get f of x is equal to, and we're doing an antiderivative, so now we're doing an integral, so the backwards derivative, add 1 to the exponent, divide by the new exponent, so we have x cubed, there's our new exponent, 6 divided by 3 is 2, minus 5, so minus 5x, you're just adding in a little x there, and we have to put a plus c. Do not disappoint your teacher, put that plus c there. In fact, that's where my name for Twitch comes from, vitamin plus c. That's the whole joke. Anyways, finishing up here, we have f of 1 is equal to 3, so if I plugged in a 3 there, I get 2 multiplied by 1 cubed minus 5 times 1 plus c. We got 3 is equal to 2 minus 5 plus c. 3 is equal to negative 3 plus c. You got 6 is equal to c. And finally, for your final answer to the question, it wanted us to figure out the original function. So f of x must in fact be 2x cubed minus 5x plus 6. Done and done. Moving on to number 18. We got some objects. We've got a height, t seconds, all this stuff. If you don't have this paper in front of you, this is what it says. An object initial height, negative 5t, blah, blah, blah. What is the initial height of the object? Velocity, all this kind of stuff. All right, here we go. 18. So we have h of t is equal to negative 5t squared plus 20t plus 80. And yeah, initial height of the object, A, that's just this number over here, 80 feet. 80 meters. Okay, letter B, that's done. That's the initial height, you just plug in 0. After that was the object velocity after 3 seconds. So our velocity, by definition, velocity is equal to our derivative of height. So our h prime of t is going to be negative 10t plus 20. That's a t. And yeah, after 3 seconds, so h prime of 3, that's going to be equal to negative 10 times 3 plus 20, and that is going to be equal to negative 10. Don't forget, what is it? Meters per second. Meters per second. Easy peasy. What is the object's maximum height? So anytime you want to find a maximum, you take a derivative and you set it equal to 0. So we are again going to be using our same derivative function, but we're going to be setting it equal to 0. So negative 10t plus 20. I think it's pretty trivial that t is going to be equal to 2. And we want to find the actual maximum height. So now we're going to plug 2 back into the original equation. So that's going to be h of 2 is equal to negative 5 times 2 squared plus 20 multiplied by 2 plus 80. What's that going to be? 4 times negative 5, negative 20 plus 40 is positive 20, 100. Okay. And it's feet, meters. Okay. And what is the object's acceleration? The acceleration is simply going to be, by definition, acceleration is the derivative of velocity, or the second derivative of height. So our derivative function in this case is just going to be negative 10. You just did the derivative of this one up here. And, oh, oops, I already forgot my units again. Meters per second squared. Meters per second squared. Okay, cool. Done. Number 19. We got antiderivatives. We got integrals. Here we go. Number 19. Let's hop right into this one. We have the antiderivative of the sine cubed of x multiplied by the cosine of x dx. So a great tip in questions like these, if you don't know what to do in a lot of these antiderivatives, you want to use u substitution. And it looks, glancing at these, it looks like there are like 5 u substitution questions and 1 non-u substitution question. The way to figure out if it's u substitution or not is if you notice a derivative of one part of the function is inside the function. In this case, the derivative of sine is cosine, and that's how you know that u is going to be sine of x. And therefore, our du is equal to the cosine of x dx. And when we slot this guy in, we're going to slot the u into here. So now we have the antiderivative of u cubed. And then du, because cosine of x dx is in fact du. The antiderivative of u cubed is adding 1 to the exponent divided by the new exponent, 1/4 u to the 4th plus c. Do not forget your plus c. Do not disappoint me. All right, 1/4 u to the 4th. And u to the 4th, u is sine of x. So the sine to the 4th of x plus c. Boom, boom, boom. I wonder if they put plus c's in the answer key. I don't remember seeing them. Watch them not have it. Okay, they put the plus c. That's good. That's good. All right, just double checking. Didn't have the faith, you know? Sometimes that happens. All right, we're moving on to our next problem. We have the antiderivative of e to the x multiplied by e to the x plus 1 to the 4th dx. So yet again, you want to make your inside equal to u. So in this case, the derivative of e to the x plus 1 is e to the x. So our u is going to be e to the x plus 1. Our du is going to be e to the x dx. And plugging this in, our antiderivative now is going to be the, you have e to the x dx, that's your du. You have u to the fourth du. Antiderivative of that is going to be 1/5 u to the fifth plus c, and therefore 1/5 e to the x plus 1 to the fifth plus c. Oof, we are almost done with this entire thing. We only got a couple more, 5 more questions, guys. That was question number 20. We are moving on to question number 21. We got secant squared of the natural log of x all over x. This one might be a little bit tough to see, but in general, you want u to be the inside function, and u is the inside function here. U is going to be equal to the natural log of x, and therefore our du is going to be 1 over x dx. Simplifying this one in, we can see that we have the antiderivative of the secant squared of u du, because there's our 1 over x dx right there. This one you just have to have memorized. The derivative of tangent is secant squared. So this one's going to be the tangent of u plus c, and therefore the tangent of the natural log of x plus c. Boom, boom, boom. Number 22. Number 22, we have the antiderivative of x over x squared plus 1 du, dx, sorry. Not a du yet. Will be a du in just a moment, because I'm going to make u equal to x squared plus 1. We're going to make du equal to 2x dx. Now, the problem here is we don't have a 2x dx. We have an x dx. So there are a couple different ways you could think about it. Because differentials can be multiplied by scalars and it doesn't cause a problem, we can simply say that we have 1/2 du is equal to x dx. However, if your teacher specifically told you that you're not allowed to write that, another way of approaching it is instead saying that you're able to change this function over here into 1/2 integral of 2x x squared plus 1 dx, because all you did was multiply by 2 and divide by 2 in there. So you could just like jump right into using your du over here with the 1/2 in front, or you could say it's a 1/2 du is your x dx there. Regardless of what you do, all this information is going to combine into having a 1/2 antiderivative of 1 over u du. And then you have to have your antiderivative of 1 over u du memorized, because if you tried to make it u to the negative 1 and add 1 to the exponent, divide by the new exponent, you'll be doing negative 1 plus 1, you get 0. Divide by 0. Dividing by 0 is a problem. Antiderivative of 1 over u is the natural log of the absolute value of u plus c. But u in this case is x squared plus 1. Because x squared plus 1 cannot take on negative values, you do not need the absolute value signs for this question. If you want to put absolute value signs in your answer, you're allowed to, but again, x squared plus 1 is a positive valued function, and therefore the absolute value signs don't do anything. Kind of interested to see, do they put the absolute values in their answer? They do not. They do not put the absolute values in their answer. Easy enough. Let's move on to the next question. All right, so the next question here, we're going to have the antiderivative 0 to 1 of x multiplied by e to the x squared dx. So for this one, we have to do a little bit of extra work because you have the limits over here. The limits will need to be changed into u limits before you start the question, and then you can just do u all the way through. So in this question, we're going to have u is going to be equal to x squared. Our du is going to be equal to 2x dx. And just like before, we're going to have a 1/2 du is equal to our x dx, or again, you could do the 1/2 in front, 2 inside thing. It does not matter. But we actually have to plug in 0 into our u. So u of 0 is going to be 0 squared, or just 0. And u of 1 is going to be 1 squared, or just 1. So in this case, they actually don't change, but only because it's specifically 0 and 1. It's definitely going to change in the next question. So now we have the integral from 0 to 1 of e to the u du, with the 1/2 in front. Don't forget the 1/2, I almost forgot. And then 1/2, and it's going to be e to the u evaluated from 0 to 1. So we're going to have 1/2, big parentheses, e to the 1 minus e to the 0. And you can probably just simplify that to be e 1/2 e minus 1/2. Boom. Oh, done. Or you could have also done 1/2 e minus 1. That would have been okay as well. Either one just doesn't matter which one you do. Pick your favorite. Pick your poison. We're on the last two problems. Here we go. Question number 24. This one, I have to admit, is quite rude. Out of nowhere, you have to have your unit circle memorized, or you can't do this question. It's the only question on this entire exam where that's a requirement. I'm sorry, I'm writing sideways completely. This one does require the memorization that the antiderivative of sorry, that the derivative d over dx of the tangent inverse function is 1 over 1 plus x squared. That's just your definition of your derivative, and therefore this one is going to be the tangent inverse of x evaluated from 0 to 1. So that's going to be the tangent inverse of 1 minus the tangent inverse of 0. The tangent inverse of 1 is asking yourself the question, where is the tangent equal to 1? Or in other words, where is the sine function equal to the cosine function? That is going to be true at pi over 4. Tangent is 0 at 0, so you just get pi over 4. Boom. Done with the question. Number 25. All right, number 25, we want to find the area under the curve of x over x squared plus 1 squared between 0 and 1. So again, positive value function, so we don't need to worry about anything else other than taking our antiderivative. So for number 25, we are having the integral from 0 to 1 of x over x squared plus 1 quantity squared dx. And another u substitution, our u is going to be equal to x squared plus 1. And by the way that you could tell this previous one was not a u substitution was because there was a 1 on top and not an x on top. All right. Anyways, du is going to be 2x dx. Again, we have that 1/2 nonsense we have to worry about. And like I said before, this one actually will change when you plug in those u's, because if I do u of 1, that's going to be 1 squared plus 1, or in other words, u of 1 is equal to 2, and likewise, u of 0 is going to be equal to 1, because if I plug in 0, I get 0 plus 1. So our new antiderivative here is going to be a 1/2 antiderivative from 1 to 2 of 1 over u squared du. And u squared is the same thing as u to the negative 2. So remember that 1 over u squared equals u to the negative 2. So our antiderivative of that, adding 1 to the exponent, u to the negative 1, divide by the new exponent, which is going to be a negative 1. So you can throw a negative in front from 1 to 2. So plugging in 2 here, remember that u to the negative 1, that's the same thing as 1 over u. So in this case, we're going to have negative 1/2 minus, parentheses, negative 1 over 1, or just 1. Like that. And negative 1/2 plus 1. Let me just write it like this. I don't know what I'm saying. Negative 1/2 plus 1 is 1/2. And therefore, our final answer is a 4th. And I'm like feeling weird. Yep, that's the right answer. Anyways, I'm done. This was like an hour-long video. Peace out, guys. Have a great rest of your day. Good luck on your finals.